What's going on, everybody? So if you remember at the end of part 3, what we were talking about was kicking a ball at a given velocity and a given launch angle, and we wanted to see whether or not it cleared this 5 meters. And as you'll remember, it did not with this particular velocity and launch angles. Now what we're going to do is I'm going to ask the question, well, what is the optimal launch angle for any object moving at a given velocity? And if you remember your physics in high school, you'll be asking the question right now, well, why in the world do we need to do this video? But before we get back to that, let's hop out of here, hop into MATLAB, and code this out and see what we get. I'm going to be starting with the same exact code that we had at the end of the last video. And so please go back and watch that one if you haven't already. What I'm going to do is I'm going to go ahead and copy everything but the figure that we made at the end of that code. And we'll put this in a new file. There we go. Okay, what we did last time is we specified a distance to clear. What I'm going to do for this particular code is not specify a distance to clear, but create a variable called distance cleared. And what this is going to do is gather all of the distances that we clear as we iteratively step through different launch angles. So launch angle, you'll remember, in our last video was set at 40 because that's what we got from the problem. Now we've got a new problem. We're asking basically to optimize angle, optimize launch angle for a given velocity. Okay, so the way that I'm going to solve this problem is just by using a for loop in MATLAB, which will iteratively update our launch angle. And then at the end of every loop, I'm going to gather in this distance cleared variable the final distance cleared as well as the launch angle associated with that distance. So what I'm going to do is use a for loop, and I'm going to say for I is equal to 1 through 90. And just so that we keep all of our loops straight, I'm going to hop down to the end right away and put our end call in, and then I'm going to gather everything inside of this for loop and indent it. Let's go ahead and indent. Okay, so now we've got our for loop set up. Now for launch angle, what I'm going to do is I'm going to call, instead of 40, I'm going to call I. And so in MATLAB, in these for loops, I is just going to step through 1 through 90 in steps of 1. Now you can change how it steps through by doing something like this. So if you wanted to go, every half angle instead of every half degree instead of every 1 degree, you could do this. But we're just going to go by 1 degree. So on the first time through this for loop, launch angle is going to be 1. On the second time through the for loop, launch angle will be equal to 2. On the third time through, it's going to be 3. Fourth loop, 4. Fifth loop, 5, and so on and so forth, all the way up to 90. Now 90 is going to be straight up in the air, so it doesn't really matter. I don't really want to go beyond straight up in the air because then we're just dealing with the same thing that we calculated in the opposite direction. Okay, now the rest of this code is going to stay the same. So you'll remember we have our launch angle, we've got our positions, our velocities, there's our resultant velocity set to 5. We've got our accelerations, this is gravity in the vertical and 0 in the horizontal. And then we've got time, our sampling rate, and our iteration variable for this while loop down here. And we said while the vertical position was greater than or equal to 0, so while the ball was still in the air, we're updating time, updating our iteration variable. If the iteration variable is 1, we go ahead and get our vertical and horizontal velocities by using sine and cosine and the resultant velocity. And then we go through on subsequent iterations and calculate velocity, position, and acceleration. Okay, so the only other thing that we have to do here, this is going to do this, the only other thing that we have to do here is actually gather the data that we calculate. And I'm going to do that in that variable that I initialized at the beginning called distance cleared. And we're going to say in the iteration row, so this is in that for loop, so we're outside of the while loop, now we're in the for loop. And so on the first one, again, I is equal to 1. On the second loop, I is equal to 2. On the third loop, so on the I row, in all columns, what we're going to do is place two things. We want the launch angle, and we want position x end. So if you remember from the previous videos, this position x is our horizontal displacement. The last variable is going to be its end value. So this is going to be the maximum distance cleared. And then this is the launch angle that it's associated with. So what we're doing is we're gathering all of our launch angles and our distances cleared into this distance cleared variable. And then at the end, what we can do is we can use the built-in MATLAB function max to figure out what is the maximum distance cleared and at what angle did that happen. And so we will say max distance and best angle. And this is going to be equal to maximum of distance, not sure why it's giving me that highlight, distance cleared, right? And when you call on this built-in max function, if you give it two outputs, the first output is going to be the actual maximum. So actually what we need to do is called maximum cleared all rows of the second column, because that's where we're putting our maximum distances, is in the second column. Launch angle will be in the first column. And we'll take a look at this variable after we run the code. Okay, so anyways, we've got max. If you give two outputs, the first one is going to be the actual maximum value, and the second one is going to be its position or its index within the variable that you call, in this case, it's matrix, or actually just an array, because we're just calling a single column in. Okay, and because we know each column is going to be a degree, and we're going in steps of 1 as specified in our for loop, we know that if it's at, for example, the 45th index, we know that the maximum angle is going to be 45, or the best angle is going to be 45. Okay, let's go ahead and give this a run and see what we get. Oh, it's asking me to save. Let's go ahead and save it just right now as temporary. Okay. Let's go ahead and run it. There we go. It's tripping up for a second there. All right, so you can see this distance declared is a 90 by 2. Let's go ahead and open it and take a look at it. So again, what we have is in that first column, we've got the different launch angles that we put in. And then in the second column, we've got the distances cleared. And so you can see as we start to increase that launch angle, we've got gradually increasing distances cleared. And then at the end, what we did is we looked for the maximum value in this second column. And we not only wanted to know the value of it, but we also wanted to know its index. And so, for example, if it was at index 27, it would return this and this, right? So instead of just looking through that, we can go ahead and come down here, and we can just do a quick display. Actually, we can just see what these are in the first place, just evaluate them. So 2.54, and the best angle is 45 degrees, right? So we can make this look distance cleared. Actually, we'll say max distance cleared is going to be max distance. And because this is a number, what we have to do is call num to string. And then we will say at angle, and again, num string, best angle. Okay, so we'll make this look a little nicer for the user. Evaluate. So max distance cleared 2.5456 at angle 45. Okay, now let me show you something. We're going to come up here. Let's clear everything out. I don't know if you can hear that. There's people playing outside. There's kids playing out there. So let's go ahead and change this to 3. We'll change our velocity to 3 and see what happens. See if our angle changes, our best angle. So now we've got a smaller distance cleared, of course, because we're kicking it at a lower rate, but our maximum angle, you can see, is still 45. So why is this? And this is why I said if you remembered your high school physics, you'll be asking why we made this video. Well, it's because for a given velocity, the best angle is always going to be 45. And you can prove this mathematically without using any numbers. And I will link to a great video that does that. I don't have the tools to write out a math proof, and it's a little bit cumbersome to try to do this on PowerPoint. So I'm just going to link to a great video for that. But you can go through and use this code and kind of play around with different velocities and things like that. And you can see that this is true. If you just keep velocity the same, the maximum angle is going to be 45, or the best angle is going to be 45 to get the maximum displacement. Okay, if you like this video, you found it helpful, please like it, please share it, please subscribe to my channel. I post a lot of stuff like this, and I'm going to be coming up with some kind of fun and interesting ways to use these same principles, these same equations of motion in different ways. So stay tuned for that. You can find out more about me on Twitter, LinkedIn. You can find a lot of my codes on GitHub. You can keep watching my videos on YouTube. And, oh, you can see my academic work on ResearchGate. I always forget to mention that one. All right, until next time, keep coding.